in addition to the tools for designing your own filters using a variety of methods, MATLAB also provides a collection of uh, well widely used IR filters. Those are some kind of filters that's already been designed, but you need to provide some additional parameters in order to actually get the coefficients of the transfer functions. And there are 4 different types of widely used IR filters. One is called the Butterworth filter, and then there are 2 types of Chebyshev filters, and then you have elliptic filters. All those filters are kind of used very widely and have a very long history. So if you would like to use any one of those filters, MATLAB actually provides existing functions for you to do that. And later on, we're going to look at the characteristics of all 4 different types of filters. But if you want to sort of use those sort of very well designed filters and very well tested filters, you can just use those MATLAB functions. So that's the way that you call those filters, call those functions to generate the filters. So if you just call butter followed by n is the order of that particular filter, and then wn, if it's low pass filter, by default it's a low pass filter, right? And then wn is sort of the corner frequency in the normalized frequency range. So it's normalized with respect to the Nyquist frequency, basically. And if you want a bandpass or high pass, if you want a bandpass, this Wn has to be replaced by a vector with 2 numbers. If it's low pass, it's just a 1 number, but if it's a bandpass, then you will need like 2 numbers for it. And then you have options. Options can also tell MATLAB if you want a high pass. If you want a high pass, then you can specify the character string high in the options, and then the Wn is going to be the corner frequency of the high pass field. So if you are not familiar with any of those functions, you can just type help, say butter. Then it's going to give you detailed explanations about how to use it, either for high, low, or stop band, that kind of different kinds of filters. And you can choose to output either the coefficients for the numerators and the denominators, the polynomial coefficients, or you can choose to output the zeros and poles and the gain for that particular design filter. And then you also have another option, A, B, C, D, which basically allows you to output the state space matrices, right? The state space, if you know what that actually means, then it's going to be useful for you. But in our lessons, we haven't actually talked about the specific meanings of those things, right? And then for Chebyshev type 1, the usage is pretty much the same, but later on we're going to see the characteristics of those different kinds of filters. And then you understand what's RP and RS. So RP allows you to specify the ripples, the peak-to-peak ripples, the trough-to-peak ripples, the amplitude, the maximum amplitude of the ripples in the passband. And the unit is dB, actually. Basically, it allows you to specify what's going to be the ripples in the passband, the amplitude of the ripples in the passband in dB. And then in Chebyshev 2, you are allowed to specify the amplitude of the ripples in the stop band, right? That's one more input. And then for elliptic filters, you have the option to specify both RP and RS. Right. But the rest of the usage is quite the same. So now let's look at how we can actually use those filters to use those CAN filters to design some useful filters, right? So now let's first try out this butter function. We're gonna just use the simplest usage. We're gonna ask it to output the coefficients, polynomial coefficients in the transfer functions. So let's try a 7th order. A 7th order Butterworth filter. So if you increase the order, then you'll have more points for the filter, right? The order is going to be higher, but it's going to be more expensive to apply the filter. But the benefit is that the filter is going to be more is going to be a more accurate approximation to to the desired filter. Right? So if you increase the order, here we're just using a 7th order Butterworth filter, right? And then you can specify what's going to be the corner frequency. So let's suppose we're just using a low pass filter, right? That's sort of the simplest case for us to use this function. If we want to look at the frequency domain characteristics of this particular filter, there are two tools for us to do that. One is called FV tool, BA. Then it's going to display both the amplitude and the phase of this particular filter, FV tool. Right? It's just a plotting tool, but this time let's try something else. Let's still use FREQZ. We're going to call HBW equals to FREQZ. We're going to convert this filter into a frequency domain representation. That can be plotted. So, and then we are going to generate a new figure. I'm going to hold on to it, and then turn the grid on. And then I'm going to plot W. I'm going to use the normalized frequency. Right? And then let's use the log unit. And then let's specify the color. Let's just call it B. So this is I'm plotting it in terms of the in a blue line, plotting the amplitude in dB in a blue line. And then let me specify the range of the y-axis. Let's just go from like a -80 to say 10. Right. And then if we execute this block, oh sorry, I forgot to take the absolute value. Sorry. So that's gonna be our Butterworth field, right? An example of our Butterworth field. That's the amplitude response of that Butterworth filter. You can sort of see that it's actually very flat in the passband. It's very flat in the passband. Right. So if you actually plot it in a linear scale, suppose we just generate another figure. If you plot it in a linear scale, you're going to see that both the passband and the stopband are actually quite flat, very flat compared with the other three types of filters actually. And then for the stopband, it's also very flat, right? Butterworth filter is called the maximum flatness filter, right? Because both the passband, the ripples in the passband and the stopband is very small, so it's some kind of desirable feature. But compared with the other three types of filters, the transition band for Butterworth filter is relatively wider. Right? That's the kind of trade-off you have to sort of consider when you use any one of those. And then let's look at the Chebyshev type 1 filter. It's just a CHEBY1, right? So this time let's use some slightly different parameters. Let's use a fifth order, and then the passband ripple in terms of the dB, we want to have a 1. That's the passband ripple, and then what's the corner? The corner is still 0.1. Right, and then let's call it HC1 W equals to FREQZ BA, and then we're just gonna plot the amplitude and then if we just execute this block, we're gonna plot the amplitude in black line. So that's gonna be the Chebyshev type 1 filter. You can sort of see the ripples. You can sort of see the ripples here in the passband. And in fact, the maximum amplitude of the passband ripple is supposed to be approximately 1. So you can sort of see the peak-to-peak amplitude of the ripples. And compared with the Butterworth filter, this is Butterworth filter has a much flatter response in the passband, right? But if you look at the um, stop band ripples for Chebyshev type 1 filter, it's almost flat. So um, so if I open another figure, right? Let me just this is figure 1. We're gonna plot the amplitude in log scale, and then in figure 2, we're gonna plot it in linear scale. HC1, then plot it in black. So let me just close all the figures for now, and then re-execute this block. So that's the log scale amplitudes of these two filters, and then that's the other in the linear scale. So you can sort of see for the Butterworth filter, it's flat both in the passband and also in the stop band. But for the Chebyshev type 1 filter, it has ripples in the passband, but doesn't have much ripple in the stop band. So you can sort of blow up the stop band and see um, it's actually quite flat, very flat. Right? That's for Chebyshev type 1. So this is a Chebyshev type 1. So now let's look at Chebyshev type 2. I'm just gonna copy over this block of codes. All I have to do is to change Chebyshev 1 to Chebyshev 2. Right? And then I need to specify the stop band ripple amplitude. Let's suppose we want like 60 dB. That's our stop band ripple. And then instead of specifying the corner for the passband, I'll specify the corner of the stop band. Suppose I want 0.3. I want the corner at the stop band to be not the corner, but the stop band boundary to be at 0.3 units of the normalized frequency. And then the output is gonna be called HC2, and then we'll plot HC2 in say red color, right? And then for Chebyshev type 2 filter, you can see that for the passband it's relatively flat. It doesn't really have much of a ripple, but for the stop band it got ripples, right? And the same is true for the linear scale, but it's just slightly harder to see. But you can still see the ripples. You can sort of see the ripples on the linear scale. Right? It's for Chebyshev type 1 and Butterworth filter, it's much flatter in the stop band. So that's the trade-off that you have to sort of consider, right? And then the final one is called the elliptic filter. So we're gonna see what the elliptic filter is gonna do. So in order to again, I'll just copy it over. So in order to use the elliptic filter, what I have to do is to change the name of the filter, and then instead of using a fifth order, I'm gonna use a fourth order, and then I'll need to specify both the passband ripple and the stop band ripple, right? And for the elliptic filter, we'll just specify the corner of the passband, and then we're gonna call our output in frequency domain to be HE, right? And then we're gonna plot HE using a different color. Let's just use magenta, right? and we're gonna execute this block. So the magenta line is the elliptic filter. Right. Elliptic filter. So you can sort of see for the elliptic filter, the magenta line, you have ripples both in the passband. That's the magenta line, and also in the stop band. Magenta line, right? So elliptic filter is gonna have ripples both in the passband and also in the frequency in the stop band. Right. And if you actually look at the frequency domain response of these 4 different kinds of filters that we have looked at so far, in addition to the ripples, right? So Butterworth filter doesn't really have many ripples both in the passband, in either the passband or the stop band. Chebyshev type 1 is going to give you ripples in the passband, but not many ripples in the stop band. Chebyshev type 2 is the opposite. It doesn't really have ripples in the passband, but it has ripples in the stop band. And then elliptic filter is going to have ripples both in the passband and also in the stop band. Right. But for these 4 examples that we have looked at so far, the corner frequency for the passband and the corner frequency for the stop band is about the same. Right? It's about the same, not differing too much. And if you look at the order of those 4 different types of filters, the Butterworth filter has the highest order, right? Chebyshev 1 and Chebyshev 2 filters, these 2 types of filters have 5th order. Elliptic filter is the lowest order, it's 4th order, which means that the elliptic filter is the easiest to implement if you want to use it, easiest with the smallest cost for application basically. And but it has drawbacks. For example, the ripples in the passband and the stop band. And then if you look at the transition band for the elliptic for the Chebyshev type 1 and type 2 filter and also elliptic filter, usually it's a steeper roll-off. It's a steeper roll-off. The transition band is usually sort of narrower than the Butterworth filter, and the Butterworth filter usually has a wider transition band if you consider the exactly the same order, right? If you consider if you use 7 for Chebyshev 1 and 7 for Chebyshev 2 and also 7 for elliptic, then you're going to see that Butterworth filter has the widest transition band. That's some of the that's one of the ways for using those canned or packaged filters. Right? The input is very simple, and the output can be used to filter any kind of a signal, input signal, very easily. So if you would like to use those coefficients, to filter some kind of input signal, it's actually quite easy to do. If all you have to do is to call the MATLAB field function. So if you haven't used it before, you can just type help field. Then it's gonna tell you how to use this particular function. And oh, it's called a filter. I think it's not filter. It's called a filter. So for if you would like to apply the filter to a particular input signal, you can just call MATLAB filter function. It allows you to specify the coefficients for the numerator, the coefficients for the denominator, and then the input signal, and then the output signal is going to be stored in Y, big Y basically. So suppose we have suppose we would like to use this Butterworth filter, for example, right? And then we have computed its coefficients, right? Now let's try to generate some kind of a random signal. Let's just use let's call x, small x equals to random signal. 1000, one row, 1000 columns, for example, right? And then all we have to do is to compute the field y as a filter BA and then x. Then that's going to be the filtered signal, right? So suppose we just execute this block. that's the input signal, right? That's the input signal, and then that's the output signal. That's sort of plotted on top of the input signal. You can sort of see, because it's a low pass filter, so lots of the high frequency content has been removed, and uh, the filtered signal is plotted in red here, right? Even though it's harder to see it, maybe I should use a thicker line. That's the filtered signal. So that's how you can actually use those coefficients computed by those filter generators, right? And there's all those filters are gonna have a phase. It's a non-zero phase filter, right? So including Butterworth, Chebyshev 1, Chebyshev 2, and elliptic, all those filters actually has non-zero phase. And if you would like to sort of cancel out the filter, cancel out the phase of the filter, if you just want to use a zero phase filter, right? What you can do is to use another function called filter. So it's a zero phase forward and a reverse digital IR filter. So what this function is gonna do is that it's gonna do a forward filtering of the input signal, just like the MATLAB filter function, just like before, and then it's gonna time reverse the filtered signal, and then apply the same filter again. So this time reversal operation actually allows you to cancel out the phase introduced by the filter that you applied for the first time. And then after you have done these two forward and backward filtering operations, this function is gonna sort of reverse the output, reverse the time axis of the output again. Right. So this way you basically can cancel out any phase that's introduced by the filter. So the result is basically a zero phase filter. But one thing that you have to remember is that this filter function is basically applying the amplitude of the filter twice. So, for example, if you are using a Butterworth filter, a 7th order Butterworth filter, applying it forward and backward twice is going to essentially give you a 14th order Butterworth amplitude filter, right? So basically the amplitude of the filter is applied like twice, and then the phase is cancelled out. And if you would like to sort of use that kind of filter, what you can do is to let's say y1 equals to filter BA(x). Sometimes this kind of zero phase filter is important because you do not want to introduce any phase into your output. Now let's try to plot it. Y1, but let's try to use black line with 2. Right. So now this sort of zero phased filter is kind of a that's the so red line is like the forward filter, so you can sort of see there's a phase introduced, right? So this waveform has been shifted to this waveform. Right, there's a delay in terms of actually a group delay basically, right? But the black line has zero phase in it. So with respect to the original signal, the input signal, the black line has no phase distortion. All the changes are caused by the amplitude of the filter, right? But you can also see that if you compare the black waveform with the red waveform, they are still slightly different. The reason is that the black waveform actually has a narrower bandwidth, basically. It's because you are actually applying the same filter twice. The amplitude is being applied twice, basically. So it's actually narrower, right? It's equivalent to a 14th order Butterworth. So the corner, the bandwidth is actually the transition band for 14th order butterworth is like a lot sharper than 7th order. So that's why you sort of see the differences in the shape of those waveforms, right? So that's how you can actually get a zero phase filter by applying the Butterworth filter back and forth twice. And MATLAB actually has a function for that called field filter, right? And um, that's one of the ways for using those canned or wrapped filters. There's also a second way for using those filters. That's by calling the design field. The design field is a second way for you to actually use those different types of IR filters. And in order to use this design field function, you have to specify these parameters, basically the passband and stopband frequencies, the passband and stopband ripples that you would allow, and then uh, the it's going to output either the coefficients. It's actually going to output a digital filter object. It's going to output a digital filter object, and that object can be used together with filter or field um, those functions. So now let's look at one example. So here we're going to start to use the design field function to use those different types of IR filters, right? And in order to use those functions, we need to specify some parameters. So suppose the sampling frequency, sampling rate is basically just how many points per second you're actually sampling the input signal. So we have like 2,000, say 2,000 samples per second. And then FP is going to be the passband corner. Let's say 100 hertz. Right. This is not normalized frequency. Right. Here we're actually using normalized frequency. Right. It's all normalized with respect to the Nyquist frequency. And Nyquist frequency for this particular example is going to be 1,000 hertz. Right. It's just half of the sampling frequency. And then we need to specify what's going to be the stopband frequency. And then we're going to need to specify what's going to be the passband ripple. And then the stopband ripple. Or these ripple amplitudes are in terms of dB. And that's pretty much everything we need to specify. Then we can call the design field function. Let's use the Butterworth field first. And then the output is the object that's called dButter equals to design field. And then we need to specify the type of the filter, low pass, IIR. That's the first input they call low pass, IIR. And then passband frequency, FP. And then stopband frequency. FST. Then passband ripple. AP. And then stopband ripple. AST. And then sample rate. FS. And then design method. Butter. So that's how you actually use the design field function. And the output is stored in a object that's called a dButter. This object is a digital filter object. It's actually a MATLAB structure, basically. So if you want to run it, you can just stopband ripple is not recognized. Maybe I typed it wrong. Stopband attenuation, not ripple. It's actually called a stop band attenuation. It's not called a stop band ripple. Now it's gonna work, I think. And then this object can be visualized using FV tool. If you just call FV tool debutter, then it's gonna display this kind of diagram for the amplitude response. For this particular example, this is actually identical. This is actually identical to the blue line here, right? If you actually fix the range of the y-axis from like a -80 to like a 10, then you're gonna see that it's actually the same as the blue line. This Butterworth filter, it's actually the same as the Butterworth filter generated using this line, right? The advantage of using a design filter is that it's gonna compute the correct order for you. You don't really have to specify the order. You don't have to specify the corner frequency by hand. It's not. You don't really. Sometimes you don't really exactly know what might be the correct parameters for what might be the correct values for these two parameters. Using design field, you don't have to. You just let the system to determine what might be the best parameters for that for this particular desired filter, right? All you have to do is to specify what's going to be the frequency of the pass band, and then what's going to be the frequency of the stop band, right? And then sampling rate, and then the attenuation level in the pass band, the ripple level, the level of amplitudes in the level of the ripples, the amplitude of the ripples in the pass band and the stop band, basically, right? So if you would like to see what's actually the order of the filter that's being produced, you can use another function that's called field order. Called field order, FILTORD. You just send this filter object into a field order, then it's gonna print out what's actually the order for the design filter. So if you do field order, it's gonna tell you it's a 7th order. It's a 7th order filter. Right. So now let's try to use the same design field function to generate the other 3 types of filters. We're gonna do Chebyshev 1 first. I'm gonna just copy over this line and then change a few parameters, and then I'm gonna call it dCheby1. Copy this line. I'm gonna call it dCheby1. All the parameters stay the same, but the design method has to be changed. Instead of butter, I'm gonna use CHEBY1. Cheby1 is the name for that particular method. And then I'm gonna again copy all the parameters over, but this time I'm gonna use Cheby2. The method is Cheby2 now. And then I'll do that again, but this time it's gonna be an elliptic filter. I'm just gonna call it dellip, and then the method is ellipse. And then let's look at the filter order, right? So field order allows me to compute the filter order for each of the different filters. I'm gonna store it into a vector. And then in the FV tool, I'm gonna put it into a FORD. for the FV tool, it can accept multiple filters. So I'm gonna use dbutter and then dcheby1 and then dcheby2 and then dlip. Right. Then now let's take a look at the output. So if I wanna rearrange change the volume, then maybe that's a better looking figure, right? And for the filter order, you can sort of see the Butterworth filter actually has the highest order. It's a 7th order filter. And then for the Chebyshev 1 and Chebyshev 2 filters, it's a 5th order. And then the elliptic filter actually has the lowest order, 4th order. Right? So the Butterworth filter is probably the most costly filter. But you can sort of see it has some desirable features, right? So it's flat both in the pass band and in the frequency band, stop band, right? But it's a roll-off. It's slower. The transition band is wider compared with the other 3 types of filters, right? And this FV tool actually plots all of them in a different color, right? So let's try to put the legend on. Right. So now let's in order to actually use the legend, I need to sort of put this put the output of the FV tool into another object. Let's just call it HFV. That's the handle for that HV function, right? And then I can do a legend HFV, and then I can just Butterworth Chebyshev 1, Chebyshev 2, and then elliptic. If I just execute this line, oh, I see. I need to actually execute the whole block. So now it's gonna give you a legend. Give you a legend. So blue line is the Butterworth filter, and then Chebyshev 1 is the green line. Chebyshev 2 is the red line, and then the last one is the elliptic. Right. So all those 4 filters actually satisfy this set of parameters given by the user. But depending upon your preference for a specific application, these 4 different types of filters actually gives you different kinds of a response. Right? Amplitude response. And so if you don't like the phase, you can cancel out the phase by using a filter, right? Just like the example that we did before. But the order of the filter is going to be like twice as high. I mean, the order of the amplitude response is going to be like twice as high. It can get rid of this command is going to remove any phase introduced by the filter, right? But if you don't want to cancel out the phase, you can choose the filter that gives you the minimum distortion in the passband, for example, in terms of phase. And if you want to sort of look at the phase of the different tools, you can add some options to the FV tool function. So we're gonna do analysis. FV tool actually has the capability to do some analysis. It's not just a visualization tool. It can actually compute some additional parameters that might be useful. So the analysis we are gonna look into is the group delay. Basically, we would like the filter itself to has a smaller group delay in the passband, for example, right? And for group delay, it has a name that's called GRPDELAY. GRPDELAY. So let's try to look at the group delay for these four different types of filters. That's sort of the group delay response. Of those four different types of filters. For group delay, what you would like to have is something that's relatively flat, relatively smooth in the passband. It's basically the group delay is basically the derivative of the phase of the filter with respect to frequency. So the reason that you are seeing this kind of a large amplitudes at the boundary of the passband is just because the change in the phase across this passband, across the corner of the passband is relatively large. So the derivative is a reflection of that big change. Right. So that's why you see the peak of the phase derivatives, the group delay, basically the phase derivatives, is kind of maximized at the corner of the passband. Right. But if you care about the phase across the passband, you're gonna see that the Butterworth filter and then the Chebyshev 2 filter. So basically the blue line and the red line, has simpler shape. Right? They are relatively flat. They are relatively flat for the passband. So if you really care about the phase of the filter, and you don't want to use the field function to cancel out the phase of the filter, to zero out the phase of the filter, to get a zero phase filter, then Butterworth and Chebyshev 2 give you better behavior for the phase in the passband. Right? That's the second consideration that you have to make when you choose the appropriate filter for your particular application. And in addition to the amplitudes and the group delay, analysis, a third thing that might be interesting to do is to look at the poles and the zeros of all those different kinds of filters that you have constructed. And FV tool allows you to display the poles and the zeros also. So that's this line. You basically give FV tool the four different types of filters you just constructed, and then in the option side you can specify pole 0, and then it's going to display all the poles and the zeros of those four different types of filters. And by looking at the poles and the zeros, it's possible to anticipate what's going to be the behavior of those different kinds of filters. And so all the zeros for different kinds of filters are in circles, right? And then poles are in crosses, and they have different color, right? So Butterworth is blue, right? And then Chebyshev 1 is like a green, that kind of thing. And because it's a low pass, so you can sort of see all the poles are kind of clustered around here. But different filters are going to have the location of the poles are kind of different, right? So the red curve is Chebyshev 2, right? That's the red curve, red crosses, poles for the Chebyshev 2, and then the blue crosses are the poles of the Butterworth, right? And then this the green crosses and the cyan crosses are sort of elliptic, and the Chebyshev 2 poles, they are clustered here, right? So if you actually goes around this unit circle that's basically ranging through all different frequencies, then at this kind of a frequency range, the angle is basically the frequency, right? At this kind of frequency range, you'll be able to sort of get a large amplitude for the filter. But the distance to the poles basically decides how big it is, actually, right? Um, so for the Chebyshev 2 and for the Butterworth filter, these two sets of the distance is relatively farther away, right? But for the Chebyshev 2 and the elliptic filter, the distance is relatively close, right? So, and then the locations of zeros are kind of distributed around the unit circle, right? All the poles are strictly inside the unit circle, so it's a bounded input, bounded output. All of them are actually bounded input, bounded output filters, right? But the zeros are kind of right on the unit circle, right? Right on the unit circle. So, uh, so the location of the zeros also has implications about the ripples and the amplitude of the filter in the stop band, right? Close to or around the slot, throughout the stop band. So pole zero diagrams are some kind of useful for you to compare those different kinds of filter and understand their differences. So one of the metaphor for filter design, basically the things that you need to consider in filter design is the three things basically: filter order, the width of the transition band, and also the ripples in the pass band and stop band. These are the three things that you have to consider, but they have trade-offs. Just like in a triangle, the summation of the three angles must be equal to 180 degrees, right? If you actually increase one of those one of those one of those angles, it's gonna have impact on the other two factors that you have to consider. So if you actually fix the filter order, then you have two things that you can sort of consider. One is the transition width, then the other one is the ripples, right? So it's often the case that if you increase the transition width, you can sort of reduce the ripple amplitudes, and if you actually reduce the ripple amplitudes, you may have to increase the transition width, right? So there's a trade-off between these two, and um, for different kinds of filters or different types of filters, the trade-off might be different, right? Could have different kinds of trade-off, and you also have to decide what's going to be the important factors that's specifically that's important for your specific application, basically, right? And because of the computing power is actually increasing these days, so and if you are actually doing digital filters, right, it's not an analog filter, it's a digital filter that you can actually use in MATLAB or something. Filter order might not be really that important. You can increase the filter order to some very large numbers, and the involved computational cost is really not that high for today's computers, right? So filter order can be higher if you have to sort of come up with some kind of compromise, right? And and this kind of metaphor basically accounts for the three most important things that you have to consider when designing either a FR filter or a IR filter, right? All of them, all those three things that you have to take into account, and uh, those design specifications is of course application dependent. Um, for different areas or different kind of applications, uh, you may have different kinds of requirement for each of those three factors.